Okay, so let's just go. I'm just going to try to clarify a few points for you. The first, the continuum hypothesis. What is it? The continuum hypothesis seeks to answer the question, is there one set that is larger than the integers and smaller than the real numbers? That's the famous continuum hypothesis. Cantor's continuum hypothesis is that there is no such set. The mathematics after Kant, through Paul Cohen, demonstrated that the continuum hypothesis is independent of the zero-Frankel axiom, and in that sense, unprovable. But remember, a mathematical proof demonstrates the unprovability. Now, that's extremely important to what makes it a mathematical proof. You don't just assert that it's unprovable, you show how it's unprovable. Yet Cantor assumed that it was true, even though he himself could not prove it, and other mathematicians demonstrated the formal independence of the continuum hypothesis from the zero-Frankel axioms of set theory. What Cantor did successfully demonstrate in his famous proof for the diagonal argument that suppose that one cannot put real numbers and integers into one-to-one correspondence, one of the most beautiful proofs in modern mathematics. This is in part, as we know, because a typical real number is characterized by infinite expansion, or more precisely, through infinite decimal expansion. Put somewhat differently, there are real numbers which are not computable by the inaugural. And there's a lot of people now who are doing work in computer science looking for the inaugural. Normally, we think that being able to specify a number is being able to compute them. But this is not the case in real numbers. And therefore, it's impossible to put real numbers and integers into one-to-one correspondence, which Cantor definitively demonstrated in his proof. This is what made Cantor famous as a mathematician. The question remains, however, is there one set that is larger than the integers and smaller than the real numbers? This is a different question than the one Cantor demonstrated in his famous proof, and it's this question, the continuum hypothesis, that he never succeeded in proving. As a Platonist, however, the then unprovability of the continuum hypothesis did not prevent Cantor from assuming its truth and from trying to show how it could work in other axioms. Even the later demonstration that the continuum hypothesis is independent from the zero-Frankel axiom would not necessarily keep a Platonist from assuming that someday he might be able to prove it, because mathematical truth is the realm of transcendent being, it's simply there, and even if we cannot grasp it. And I read to you the very specific these are mathematicians who are Platonists defining what Platonism is. What's key then is what Cohen did. A good mathematician wants to leave behind the specificity of the unprovability. It's not just enough to show it as independent, to show exactly why it's independent, because then the next mathematician can pick up from exactly where you left from. Let's turn to the background of the original question. And I tried to get into this whole debate about the infinite and finite through one of the questions that Cantor obsessed about. How many points are there on the line? Set theory, by the way, is about numeration and numerability. That's how it started. That still remains its obsession. How many points are there on the line, and why is it so hard to resolve? The strict finitist does not recognize any mathematical use of infiniteistic notions or infinite methods, summing up an infinite series, for example. The strict finitist might want to distinguish between small and large finite numbers, arguing that there's a finite upper limit on numbers with which we can deal intelligibly, although there may be much debate about how such a limit can be set and determined, and this is all the latest debates in computer